Hey guys, today we're going to take a look at scatter plots and linear correlation. So this is us getting into sort of this is real statistics. This is the good stuff. So I think you're really going to like this stuff. And if you don't, whatever, that's fine. So anyway, first thing we're going to talk about, for the following situations, we're going to sketch a graph of what you think it might look like. So we've got drinking alcohol and our chances of getting in a collision. Not our chances, we wouldn't drink and drive, obviously, but somebody's chances of getting in a collision. So the idea here is that, if you don't really drink alcohol, your chances of getting in a collision are fairly low. And as you drink more, your chances of getting in a collision increase higher and higher and higher. Okay? So that's kind of what that would probably look like. Okay? If we have the amount of hours a student watches TV and their grades. Now, here's an example. So in general, probably if you're not spending your time watching TV, which I realize that's a dated reference, I should make it Netflix, but whatever. We're going to, your grades, you might see a trend of grades going down. Now, it's probably not going to be as sort of as narrow as the alcohol and crashing, because that's going to be pretty substantial. This one's probably going to be a little bit more spread out because it doesn't necessarily mean that. And of course, you're probably going to have a few people that watch a ton of TV and still manage to do quite well. And you're probably going to get a couple people who don't watch any TV but still don't do very well because who knows what they're doing, right? So anyway, so there you go. So you still have this trend, but it's probably going to be a little bit more spread out than drinking and driving, okay? Height and weight of a student. Generally, the more somebody, or the taller somebody is, the more they weigh. And actually, it's actually quite dramatic. People don't necessarily realize how much weight height adds. But so, the heighter you are, or the taller you are, the more you probably weigh. So the same kind of idea there, okay? But then we've got something like this, where if we take a person's height and the sum of their telephone, or of the digits in their telephone number, well, the two things aren't related, right? And so what you're going to see is you're just going to have a bunch of dots all over, and there's not really going to be a pattern at all. Okay? And so it's just going to be a mess of dots with absolutely no pattern whatsoever. Okay? So now we're going to sort of talk about like how we can measure these things and things of this nature. So let's see. So in data analysis, you are often trying to discern whether one variable is the dependent the dependent variable. Okay, the dependent variable. Oh, I spelled dependent wrong. That should be an E. Dependent variable is affected by another variable, the independent variable. Independent. There we go. Independent variable. Variables have a linear correlation. It's hard to write when I'm this far zoomed out. Correlation. Okay. If changes in one variable tend to be proportional to changes in the other. They have what we call a perfect positive linear correlation. Perfect positive linear correlation if y increases at a constant rate as x increases. Okay, so if they make an exact line, that's called perfect positive correlation, assuming they're going up. It's a perfectly straight line going up. If, of course, it's a perfectly straight line going down, we call this perfect negative. So perfect negative. Okay, a perfect negative linear correlation if y decreases at a constant ratio as x increases. This should be a rate, not ratio. Rate. There we go. Fixed. All right, in a scatter plot, we sketch the independent variable on the x-axis, or the horizontal axis. The only time that's not done is if you take economics, which is why I did not do well in economics, is because I couldn't get my head around the independent variable being on the y-axis, because that's ridiculous. Anyway, we put the dependent variable on the y, or vertical axis. Okay? The line of best fit, is the straight line that passes as close as possible to all the points on the scatter plot. The stronger the correlation, the more closely the data points cluster around the line of best fit. Okay? So let's jump over to the next page. And we're going to talk about the correlation coefficient, which we write as an R. Okay? So the correlation coefficient gives a quantitative measure of the strength of a linear correlation, or how closely the data clusters around the line of best fit. It will always be between -1 and 1, and if you get a value out of this range, then you have messed up because it is impossible, okay? So in other words, this is just giving us a number so we can tell how strongly something is, the correlation is, okay? So on one end, we have 1, which means it's super strong, okay? Super strong, or it's actually perfect. If it's exactly 1, it's a perfect correlation, makes a perfect line in a positive direction. If you have -1, it's also perfect, but that's in the negative direction, okay? If you get a correlation of 0, or correlation coefficient of 0, that means there's absolutely no correlation whatsoever, okay? So we've split it up, and so if you have between 0.67 or -0.67 and -1, so that's going to be strong, okay? That's going to be very strong, and that's at both ends, okay? It's strong on both ends, okay? If it is between 0.33 and 0.67, or -0.33 and -0.67, this is what we call moderate, okay? Moderate. Okay, moderate correlation. And if it's between 0.33 or -0.33 and 0, that's going to be a weak correlation. So often when you get a weak correlation, it means the variable is not actually, there is no actual correlation, it's just through sort of randomness that it kind of has a little bit of a trend to it, okay? And then of course, if it's in the negatives, it's a negative. And if it's in the positives, it's positive. So negative, negative, and negative. And then over here we have our positives. So positive, positive, and positive. So when you go to describe, if I ask you to describe a correlation, this is what you're going to give. You're going to decide, is it strong, moderate, or weak? Is it positive, or is it negative? Okay? So using algebraic manipulation and the fact that the sum of all the data is n times the average, or the mean, Pearson showed that R is this. And how did he show that? I don't know, because he was a lot smarter than me. So the formula is also known as Pearson's R. Most people just call it the correlation coefficient, though. Okay? So we're going to do an example here. We're going to show how to use this. So to begin with, we're going to draw the scatter plot. Now, unfortunately, drawing straight lines is extremely difficult because I can't really use, oh, see, I'm trying to use a ruler, and it's not. So, oh, wow. It's a disaster. All right, so I'm just going to draw a non-straight line that's supposed to be straight. And of course, you will use a ruler, but I'm just going to try and do my best. That's actually not that bad. I thought I would do way worse than that. Okay, so I'll tell you what I'm going to do. I'm just going to plot this data on the graph. I'm going to pause the video for it so that you don't have to sit there and watch me painstakingly write this out. Okay? I'll be back. And we're back, and there's my completed graph. It doesn't look great. It turns out it's really hard to do this on a tablet. But anyway, so if we take a look at it, we're going to try and classify this linear correlation. And so just by glancing at it, we can kind of see that it's kind of decreasing actually. So it's probably going to be a negative correlation. How strong that correlation is, it's hard to say. I don't think it's weak because there's definitely a clear direction, but it doesn't look strong either. So I would guess that it's in the moderate, but that's just an estimation, okay? And so now we're going to actually do the math and find out what it really is, okay? So let's jump over here. So what I'm going to do, because I have to do that big formula, so what I like to do is I like to go through and just say, you know, what all the different things are, okay? So, or like what the actual values are. So the first thing, we need to know what n is, okay? So what n is the number of data points. So I'll write that over here. Number of data points. Okay? So there's 7 data points, so this is going to be 7. I should check it and make sure that I used the right data set, which I did. Okay. I have been known to use the wrong data set when I do it on my own, and then my answers are off. So the next thing we need to know is the sum of x times y. So remember, this is where you take each x value, multiply it by its corresponding y value, and then add them all up. Okay, so I have done this ahead of time. And so if you're uncomfortable with this, I do recommend that you actually try this yourself. Maybe pause the video and try each of these and make sure you can get the right numbers. But what I got was 5,083. Okay. Then I did the sum of just the x's. So I just take each of the x values and add them up, and I got 69. Okay. Then I did the sum of the square of each of the x values. So I just squared each x value, added them all up, and I got 823. 823. Okay, so then I did the sum of all the y values, which gave me 500. Whoops, I don't know what that was. 533. And finally, I added up the square of all of the y values, which gave me 41,067. Okay, so that was all the pieces that I need so that I can just actually sub it into the formula and find out what I get. So we'll start by writing out the formula. So R equals, I'm going to zoom right in, try to make this as neat as possible because it is a pretty messy equation. Obviously there's not an equation that you're going to love doing, but fortunately I'm going to teach you how to do it on the computer, and then that'll speed things up. But in the meantime, we do have to do it the long way. Okay. And so then we got the square root of n times the sum of x squared minus the sum of the x, whoops, what was that? Squared, and then we've got n sum of the y's squared minus sum of the y's squared. And there we go. So now we just go in and we sub in all the numbers. So we've got 7 times 5,083 minus 69 times 533. Okay, and then we've got divided by the square root of 7 times 823 minus 69 squared. Okay. Times 7 times 41,067 minus 533 squared. Okay. There we go. So when you actually go to solve this, my recommendation is to do solve for the top, solve for this guy, and solve for this guy independently. And then just, I don't know, I think that's the best way to do it. It's such a messy formula that if you just try and do it all in one go, or if you try and do it, you know, any other way, you're just likely to mess it up. So that's how I recommend it. I did that way, and I got on top, I got 1,169 or negative 1,169. On the bottom, I got square root of 1,000 times 3380. Okay, and then that is nice and easy to put into a calculator, and I got negative 0.65. Okay, so that's what we're looking for. So can we make any conclusions? Well, there is it's a negative correlation, and it does fall between the 0.33 and the 0.67. It's at the high end, but we're going to say it's moderate because it is in that bracket. If we had a ton of data, I would say that it was bordering strong, but there's only 7 pieces of data, so I don't really think that it's fair. And obviously, I mean, doing it by hand, if we had more than 7 pieces of data, it'd be the worst. It'd take forever. But anyway, so therefore, there is, I'll zoom in so I can try and make this a little neater, a moderate negative correlation. All right. And there we go. So that's all for today. So until next time, go Sabres.